Hey everyone. So let's go. Today we're going to do interference and standing waves. So we're going back to the PowerPoint thing. There's a lot of sort of animations and drawings that I wanted to bring up. So for interference, okay. So let's talk about when objects collide. Um, and we'll start with when objects collide, like everyday objects, like this video here on the left. We have two objects colliding, and when objects collide, like you've seen objects collide before. When they collide, they hit each other. Sometimes they bounce off of each other, like we have here. Sometimes they'll stick to each other. You may remember from your momentum unit, right? Sometimes that's a thing that happens. But in the end, they behave like objects do. Like they have this sort of very intuitive behavior when they crash. Now, waves do something totally and completely different. When waves collide, they don't like bounce off of each other or stick together. What they do is they combine or interfere with one another. They sort of like combine and then pass right through each other as they go by, which objects do not do. To put this into context, let's say you're walking down the hallway and another student like bumps into you. Right, the two of you just crash into each other. When you do that, you crash into each other. Like you fall to the floor, maybe you spill your books, and you know, whatever. But what waves do, which is a little different, is they would combine each other. So like literally, you would crash into that student, and you would just combine into like a super student person. And that's what waves do. Like it sounds weird because it is. Objects do not do this. So it's just this very different, strange thing that waves do. So when two waves collide, they combine or interfere is the word we have for this combining of waves. The resulting wave pattern can be found using, new word here, superposition, which is like a fancy physics way of saying adding. When you use superposition, you are just adding the two together. After interfering, the two waves pass through one another unaffected by the collision. So if we were trying to use this like you walking through the hallway analogy, if you were waves, you'd almost act like ghosts. Like you would just kind of like collide, interfere with one another, and then just go happily on your way as if you never even touched one another. You just go right through one another. So again, here on the left we have our objects, which behave like objects do. I'm going to lose that because I feel that it may be distracting you. And we're going to focus on this guy over here. Which is no longer animated for me. So, notice that, I just missed it. We'll wait for them to crash again. So here we've got two waves, one up, one down. When they collide, they're going to combine together, and then see how they just kind of like go right on by each other as if it never happened. But the moment when they do collide, notice what's going to happen here is they'll combine to make this larger sort of downward waves. So they combine while they're overlapped or while they're in that state of collision. But once they're done colliding, ready, watch this, they combine, they're upwards. And once they're done colliding, they just kind of continue on their way as if it never happened. We call that interference. There's two types of interference, constructive and destructive. We'll start with constructive first. Constructive interference is when two waves interfere to create a larger wave. Both waves, in order to be constructive interference, both waves either have to be positive, meaning upwards, or both waves have to be downwards, which we would consider the negative direction. So here, don't worry about these units. This was just like the handiest thing I found in Google for this. Let's start, well, I timed that really bad. So let's start with constructive interference when they're, no, that's going to be destructive. So let's look at these two waves when they're both in the same direction, meaning when they're either both up or both down. I'm looking at this diagram down here. So for now, they're both downwards, right? So they collide, and I want you to notice right when they combine with each other, see how it gets really big right at that instant. That's constructive interference, because two smaller waves made a bigger one. When they're both upwards, notice right now, when they combine, see how they got really tall right at that one instant? Again, they constructively interfered with one another. Over here, I freeze framed them both, and it took me a long time to get them just right, and I still didn't quite get this bottom one here. But notice that as they're about to collide, see how they both have an amplitude of 0.5? Like that's how far up or down they go. So we'll do that again when they're both in the positive direction or upwards right now. There we go. They both have 0.5. See, when they combine, they went all the way up to here. And again, I paused it or freeze framed it for you here. 0.5 and another 0.5 made a total of 1. That's superposition. We just added them. That's all that word means. When they're both downwards, like they're about to be right now, and they collide, see how they go all the way down to -1? I missed it. I spent like 10 minutes trying to freeze frame it perfectly, and I still could not do it. But again, so the idea is that we had one that was like -0.5, the other was -0.5. Well, -0.5, -0.5, what did those make? -1. When they were colliding with another, we had +0.5, +0.5, and when they collide, they make +1. Constructive interference. Two smaller waves combine to make a bigger wave. So, that's constructive interference. The opposite is destructive interference. This is when two waves combine to cancel each other out. This will happen when one is positive and the other is downward. So, like right here, we're about to have it at this instant. Ready? Right there. It happens very quickly, so it's a little hard to catch. So I tried to freeze frame it at like one of the instants where they perfectly overlap. So we've got, again, as they collide, we've got +0.5 and then -0.5, just like we have. Oh, they went away. Just like we had there. All right, +0.5, -0.5. What do you think those should combine to make? Well, and positive, negative. What do you think those should combine to make? I would say that those should combine to make, well, 0. They should cancel each other out, positive and negative. And so again, I spent like 10 minutes trying to freeze frame this perfectly, and I could not. So this is the two. But you do see that as they're mostly overlapped, they cancel each other out. Notice that this is definitely a lot smaller than the two individual ones were. So it is possible to totally cancel each other out. If they totally cancel out one another, you would have a perfectly flat line. And in fact, there is a perfectly flat line at some instance, when they're perfectly overlapped, because they destructively interfere. They cancel each other out. So that's destructive interference. Two waves that combine to cancel each other out. Okay, I tried my best there, but this video does it actually a little bit better. So I'd like you to go to this video, watch it, answer the questions as it goes. Each of the answers are time-stamped, so, watch the whole thing. But these are like the important parts that I really want you to get and to focus on, are these questions. I'm going to go over the questions at the end. But answer the questions, follow along with the video carefully. The guy does a really good job of explaining all of these ideas. Okay, so I'm hoping you can watch the whole video, answer the questions as you went, or at least follow it along. So for starters, are waves objects? No. Oops. The answer is no, they are not objects, which I tried to mention at the beginning. They just behave differently. They're like a different sort of thing, is what I was trying to point out. At the 1:30 mark, two waves are shown to collide and add together. When they add together, this is an example of constructive interference. So again, I gave you the definition, but he gives you like a nice example of it. It's nicely illustrated. What is superposition? Well, if you wrote anything, I forget the exact wording he had there, but basically it's the addition of waves. And that's what superposition means. So again, it's this interference. How do you find the resulting waveform or what it would look like? You just add them together. So anything you wrote along those lines, the addition of waves. At the 2:57 mark, two waves are shown to collide and cancel out. So I had trouble freeze framing it before, but he did a really good job of freezing it right at that moment of destructive interference. This is an example of, I just said it, destructive interference. The two waves combine to cancel each other out. Not for a long time, which is why it's hard to freeze frame it at that moment. And I think he brings it up. It's hard to catch that moment of total destructive interference. But again, they cancel each other out. As long as one's positive, the other's negative. At the 350 mark, the interface of the two waves is shown in pause. What do you notice about the amplitude of the destructive interference? I'm hoping you wrote one of two things. You either wrote small or 0. What I'm trying to do there is relate this term amplitude to destructive interference, is what I want you to catch on to. And the idea is, again, at that moment where he pauses it and shows you that destructive interference, I'm hoping you notice that they largely cancel out, which gives you a very small amplitude resulting wave. So if you watch that whole thing, again, I think it's helpful. It brings up a lot of the same ideas, but he illustrates it very well. All right, Regents questions, right? What good is all the information if you can't answer the test questions? So, good multiple choice here. The diagram below represents two waves traveling simultaneously at the same time. In the same medium, at which of the given points will maximum constructive interference occurs? All right, well, constructive interference occurs when they were either both upwards or both downwards, because then they'll combine or add together in the same direction. Based on that, I think B is out. See how one's positive, the other's negative? I think those will destructively interfere or cancel out. So B is out. I think A is an example of constructive interference. I think C is an example of constructive interference. I think D is an example of constructive interference. But at which of these points do you think will get the most constructive interference? I would say the one where they're both the biggest. The answer to this is D. Because they look like they're both like all the way down. They're both at that maximum negative amplitude. That means they'll combine to make the biggest value downwards. That one, the answer was D. Question 10. The diagram below shows two pulses approaching one another in a uniform medium. What will be the amplitude of the resulting pulse when the two waves meet in the center? Interference isn't a terrible thing. Don't overthink it. We got 5, we got 10. What will those make? Well, they're both upwards, so they will constructively interfere. 10 and 5 make 15. That's it. Drawing waveforms. Alright, pause the video and I want you to give this a shot. I'd like you to draw the interference pattern, or the superposition, and state the amplitude. Okay. You should be able to get through these three. This last one might be a little tough, but give it a shot. So pause the video, try this out. I'll give you a second to pause the video and try it. Okay, so we've got positive one, two rectangular waves colliding, overlapping. I'm going to start with this. I know I didn't tell you to do this, but I'm going to ask you if it's constructive or destructive. For this first one, positive and positive, that's an example of constructive interference, because they're both positive. So the resulting wave, when they collide and overlap, would be probably something like this, right? Two rectangles added together. A rectangle and a rectangle makes a taller rectangle. It has an amplitude of 2. Positive 2. That's it. They just add together. Here we've got these two waves. One positive, one negative. Constructive or destructive? I would say destructive, because one's up, one's down. They'll cancel out. Will they cancel out completely? I would say no. We've got a wave. It'll still go upwards. It'll still go upwards. But it'll have an amplitude of not the full 3, because again, it's getting like subtracted from. I would say it has an amplitude of 2.5. 2.5 would be our amplitude there. Here, an amplitude of +2, -2. When those are over, all right, +2, -2. What does that make? Well, actually, let's start off with this. The type of interference would be destructive, because one's up, one's down. They're combating. They're canceling each other out. +2, -2 makes 0. So kind of like in the video that you watched, these two waves combine to cancel out completely at that moment where they perfectly overlap. It doesn't last long. It's only for that instant where they're both perfectly aligned, but you will have just no wave at that instant. Last up, I like this one. We got some weird shapes here. So you don't have to lose your mind over this one. But so you can kind of think of it like this. We've got a positive triangle, a negative rectangle, and the way that waves actually kind of work is basically what we're going to do is we take this negative rectangle and we're going to take like a positive like bite out of it, like literally as if this rectangle could bite out of the triangle. We're kind of subtracting shapes, like we're taking rectangle minus triangle, and so all of this gets canceled out, right? Because this is negative space, this rectangle, this is positive space, this triangle. So if I cancel out all of this, and I change the color to show what we'd be left with, we'd be left with something that goes across, down, across, down, something like that, something like that, something like this. And that's the shape that we'd be left with. And, oh no, oh no. And so that's the waveform that you'd be left with. So, it's okay if you didn't quite get that one. It's a little weird that you can add and subtract these shapes. But it is something that we use if a physicist were interested in creating like a unique sort of waveform, either as an electronic signal or a sound or something like that. You can send like two unusual sort of wave pulses into one another, and the result you get is like also unusual. So if this was something that you desired, like a wave shape or like a signal that you desired, this is a way that you could make it. You could send this triangular pulse, which are easier to make, a rectangular pulse, which is easier to make, and turn it into this like odd little, type of interference pattern. Okay, this is the diagram that I'd like you to be familiar with, so we're just going to go over it very quickly. Let me bring up what it's supposed to show. Alright, this next part isn't anything new, but it is a diagram that you need to be familiar with. And it's an overhead view of waves. So, this is an overhead view of two different wave sources we're looking at. The PowerPoint is on the left. Now on the right, this thing that looks like it's trying to hypnotize you is like a wave source that's being distributed like outwards. So like if I clear out the waves, right, see these waves coming outwards. Almost imagine like drip drops in like a large calm puddle, and the ripples radiate outwards. You could also think of this as like a speaker, a single speaker that sends sound out in all directions. Like if you have a Bluetooth speaker or like a smart home speaker that just, like an Alexa, that just sends sound out in all directions. You can think of it a lot like that. Now, it's a little can I pause this actually? So it's a little tough to kind of figure out what you're looking at. But what you're looking at is these sort of like brighter spots and these darker spots that represent the crests and the troughs, meaning like the high parts of the wave and the low parts of the wave. Now, overhead, we don't have a great way of seeing those high points and low points. So here they're like bright and dark spaces. In this diagram, which is one that you'll often see like written on paper because it's a little easier to write and print, you've got your sound source, or these two giant black dots in the middle. And then instead of like bright and dark bands, we have like the solid line, the dashed line, the solid line, the dashed line, the solid line, the dashed line. So far, we mostly look at waves from the side because that's where they look like wavy from, I guess you could say. So I'm going to turn on the 3D view and move this to the side. So far, we were directly overhead with something that looks like this. But as a 3D view, we can kind of look at it from the side and notice like these these ripples that are like moving outwards is what you would have. So, but here we're looking at two different wave sources and we're talking about interference patterns. So that's actually exactly what I'm going to do. So let's go back to our regular view and I'm going to change this to two different sound sources that both move outwards. And notice that we've got this kind of weird pattern of like, see these like little rays kind of coming outwards? Let's see what's happening with those, because that's where these waves are overlapping. So I think that those are places of interference. 3D view, and alright, we've got our two wave sources. Like if I was trying to line these up, I can't quite do it perfectly, but we've got our two wave sources. And you get this kind of weird pattern. Like, see these parts that are totally flat, like right here and here and here? Those totally flat parts, those are places, well, where these two wave sources are canceling out. Those are just giant lines of destructive interference. See, like here and here and here, where those waves are very, very big? Those must be places of constructive interference, where these two wave sources are like complementing each other and making a bigger wave out of it. So let's see if we can translate that into this diagram. Again, because kind of what you have happening is just these two different like wave sources that are like emanating outwards, just overlapping. And you need to be familiar with the diagram and understand what type of interference would be occurring where. So, let's see what we got. Here, and let's say we've got this part here. Those dotted lines, it looks like are meant to represent troughs, which is the bottom part of a wave. Alright, when the two bottom parts meet, where they're both negative, at this point, the two troughs meet. Well, if they're both downwards, they'd create a bigger downwards. Since they create something larger than the two individuals, that would be constructive interference. On the thing we were just looking at, that 3D diagram, that would be the place where the wave was very large, but probably large downwards, actually. Okay, let's look at this point right here. It looks like we've got a solid line, which is one of the crests, intersecting with a dotted line. Oh god, that was supposed to be dotted. Dotted line, which is the trough. Alright, the top part meets the bottom. The positive meets the negative. I think that is destructive interference, which is one of those places where those two wave sources cancel each other out. Alright, let's do here. The two crests meet, because again, it's a solid line meets a solid line, and I told you here that the solid line is the crest, or the top of a wave. Alright, two positives, or two crests of a wave, will make an even bigger positive, an even bigger crest, which sounds to me like, this is where my screen is dead, constructive interference. Sorry, I'm writing this with my mouse, it's going really bad. Constructive. Oh, this is the worst. I miss my smartboard. Alright, constructive interference. So that's it. That's what this diagram is about. That's what you're looking at. Okay. This next part of the NOPAC is an optional extra video. I highly recommend it, actually. It's really cool. It explains how active noise canceling works. So, like, if you go and you buy headphones, some of them have active noise canceling. It's often written as ANC on the packaging. And it explains, like, how basically sound is used to cancel out other sound. It's really cool. If you're headphone shopping and you're wondering why, like, the AirPod Pro costs, I don't know, $200 more than the regular AirPods, a lot of that reason is because it has active noise canceling. And if you're interested in what that is, I really recommend it. It's so cool. So I'm going to give you a second to pause it. If you're interested, watch it. If you don't care, no, you don't care. That's Alright, I'm hoping you check that video out, because it is cool. Right, the idea that, like, if you're on an airplane and the airplane's noisy and you want to make that noise go away, you don't block out the noise. You play other noise back at it, and it cancels it out. So the answer to making noise go away is to provide more noise, just in the opposite direction, out of phase, and it'll go away. It's cool. It's interesting. Anyway. The last part we got to do is standing waves, which is an application of interference. Okay, a standing wave is, for your notes, two identical waves traveling in the opposite directions interfere, creating a wave that appears to stand in place. So, what we have here is an animation of a standing wave. Okay, so this is an example of a standing wave. So it's a wave. Like, it has a wavy type motion to it. It looks like a wave. So let's pause for a second, and I want you to tell me which way the wave is moving. Meaning, is this wave moving to the right or to the left? What do you think? Really think to yourself for a second. See if you can answer that. Kind of a trick question. It doesn't look like it's really moving, right? Like, this part's kind of going up and down. This part's also going up and down. This part's not moving at all. but it doesn't seem to have this like leftward, rightward motion like we were talking about. It's just like this up and down, back and forth type motion. We call that a standing wave because it's not like moving; it's like standing. So what is this? What is this all about? So this standing wave, it's actually an interference pattern that we can make by taking identical waves and colliding them into one another. That's what creates this. So what you're looking at is not like a wave, it's an interference pattern of a couple of different waves smashing into one another. How does that work? Why does it work? So oops, sorry. Well, what we're doing here is we are taking two identical waves and colliding them with one another. So let's take this animation, which is a pretty good one. We've got two different waves. We've got a blue, what's the other one, red or green? I'm colorblind, so if you didn't know that, now you know it. Let's call it green. So we got a blue wave and a green wave. So a blue wave and a green wave are both crashing into one another. Now the black wave that you're looking at is their interference pattern. And notice that the black wave is our standing wave. If you just follow the black wave, that's the one that has the up and down motion. If you're following the blue wave with your eyes, I think that is moving towards the right. And where I'm getting that from is if I follow this blue crest along, it's definitely moving towards the right. If I take the green wave, I think that's moving towards the left. So we've got two identical waves just colliding or moving in opposite directions with one another. But what we're really interested in is, like, if you were watching this, like if you were watching like a rope with two different people like sending waves into the middle, the rope doesn't split in half and start doing two different things. It has a single interference pattern. And depending on when you pause this interference pattern, you'll notice a couple of different things. So let's look at this, which would be this second one. So what I did is I freeze framed it at a couple of different points. So again, this is exactly the animation that you just saw. This is the animation, freeze framed as best as I could get it, when the two waves are in phase or lined up with one another. So you see how like the green one's up and the blue one's up? Well, those would create a larger crest. And then the green one's down and the blue one's down, and those would create this large downwards trough. And then we've got them both up. So we've got constructive interference, and then both downwards, so we've got constructive interference. So you can kind of see, or what I want you to get out of this, is that these two waves interfering with one another would create this. These two interfering would create that. These two interfering creates this, and these two interfering creates that. Now, if you freeze frame it at a different point, and if you want to see if I'm right or not, see if you can pause the video right when when this animation up here is out of phase. So see if you can do a better job than I did. If you pause it at a different point where these waves are not lined up with one another, I've got, again looking down here at the bottom now, this green wave is up, this other wave is down. Well, that would make this flat. And then the blue wave is up and the green wave is down. This is flat. The green up, the blue down, this is flat. Again, I did have trouble pausing it when they're perfectly destructively interfering. But you see how they're canceling each other out now. And so, that would create this sort of flat moment for this wave. And so what you have is this wave that gets like really big and exaggerated, like here. And then it gets like really flat and muted, like here. And it just like goes back and forth between those 2 points. So that's what a standing wave is. It's an interference pattern created by identical waves colliding with one another. Just to be clear, what you would see, again, is not these two separate waves. I'll pull up a video of it, the standing wave actually right up. Okay, so here we're looking at this guy creating a standing wave, and what you see is it's just kind of going back and forth really quickly. We have these points that don't really move and these parts that go up and down. It's a demonstration that I have for you in class, but I guess this guy's going to show it to you. In slow motion, you can see that we have these parts that go up and down, these parts that stay still, and then these parts that go up and down. So again, you're not seeing this sort of like split action of the green wave and the blue wave going against one another. What you're just seeing is that interference pattern How does this guy have 7,000 subscribers? I have like 12 of you guys. And so, on a standing wave, what you need to be able to identify are a couple of different points on that standing wave called nodes and antinodes. So again, we're going back to our like simpler standing wave before we worried about the two things that created it. A node is the point on the standing wave that does not move. Here, our nodes are these are these red marked spots. Whoa, that's not what I wanted. Are these red spots right here? So this is a node, a node, a node, a node, and a node. You need to remember what those are. The best I've got for that is nodes have no motion. Right, they don't move. They have no node, no motion, node. Try my best. So they're the points that don't move. The reason they don't move is they're in a state of constant destructive interference. Remember that blue wave and that green wave that we just looked at? These guys right here? Pause this video at any point, and I guarantee you that the green wave and the blue wave will be at complete opposite points, like within this like rectangle. Meaning one will be positive, the other will be negative. A nice example is, this one is all the way in the bottom. We've got positive, negative. Those destructively interfere, so that won't move. And you can even see the one where like I almost got the constructive interference but missed it. Positive, a little bit, a little bit negative, and those will cancel out. So pause the video. And, you know, again, within this line, with this line, they will always be in a state of destructive interference. So it's just this point of symmetry there. So you have to know that nodes have no motion, and there's always destructive interference there. So if these points are the nodes, then these points right here are the opposite of that. You could say that they're the antinodes, which is the word for them, the antinodes. They're the points that move up and down, so they are the points that move. So here we've got, you know, if we're kind of writing it out, we've got like a node, we've got an antinode, we've got a node, we've got an antinode, we've got a node, we've got a, come on, we've got an antinode, we've got a node, and then another antinode, and then another node. So always going to form this like na-na-na-na-na-na-na-na-na-na-na-na-na Batman sort of pattern of node, antinode, node, antinode, node, antinode. Always kind of alternating. Now, you can draw a moving animation, which is actually what these all look like. So what you have to kind of do is draw it, something that looks kind of like this, and this is your typical representation of it. You'll have like a, you start at the end, you draw a wave, and then so that would be like the wave in one position, like where it's like up and down, and then you kind of like draw it in the other position. It's often a dotted line, but doesn't have to. Oh wow! I'm gonna draw it in a different part of the screen here. Sorry, just ignore that. So you might draw something that looks like this, and then the opposite would look kind of like this. Oh man, that's really meant to be dotted. To show that that's the wave in the other position. So it's like, you know, the one part and then the other part. I'm trying to draw something like these. So I could ask you not a whole lot about standing waves, actually, to be totally honest, after going through all that. I would ask you how many nodes there are in each of these drawings and how many antinodes. Pause the video, see if you can answer this. I think you can do this one here. Give you a second to pause and answer. Okay, how many nodes, how many antinodes? Let's count them up. Let's do the nodes first, and then we'll do the antinodes. Nodes. And then antinodes. Alright, nodes. So we've got, for the nodes, they're the points that don't move. They're this one. 1, 2, 3, 4, 5. 5 nodes. The antinodes, we've got 1, 2, 3, 4 antinodes. That's it. For the nodes on this one, we've got 1, 2, 3, 4, 5, 6 nodes, and then 1, 2, 3, 4, 5 antinodes. I hate to say always, but usually there will be one more node than antinode. At a more advanced level of physics, that's not true, but for us, it's pretty good rule of thumb. But I also want you to be able to draw them. So I want you to take a moment to draw a standing wave with 2 antinodes, and then I want you to draw one with 2 nodes, and then we'll be all set for today. And pause the video, give it a shot. All right, 2 antinodes. Remember, those are the parts that go up and down. So when I do this, I think the nodes are easier to count. Like, they're just these solid dots. I always felt. So we've got a node. All right, and this would be an antinode, the part that went upwards. But we want 2 of those. I'm going to do one and then a second one. And I think that would be it, right? Because we got an antinode and then an antinode. For a standing wave, you often draw the top state and then the bottom state. So, I don't know, something looks kind of like that, maybe. And, again, so these parts are the parts that go up and down, the antinodes, and then these nodes are the parts that stay still. Cool, so this has 2 antinodes again. Antinode, antinode, and these are the nodes, the nodes, the nodes. Alright, draw a standing wave with 2 nodes. I like starting out with the node. So we're going to go up, and then we're going to hit our second node, and that's it. That's the amount of nodes that I told you to do. So this one's going to go like that, and there we go. 2 nodes. Node, node, antinode. Alright, and that's it for our standing waves. 1 or 2 of the quest problems are like a little more complicated than this, so see what you can do with them. If you have trouble, please email me. Yeah, but that's it.